Okay, we are continuing our quest to find the integral from 0 to 2 of 2x dx. We have determined that it is the limit of this Riemann sum. And I want to point out that once you've got your limit of your Riemann sum set up, we basically have the limit of a sum of an area. So I've got these parentheses to sort of section things up. I'm calculating areas, then I'm adding them up, then I'm taking the limit. Okay. In simplifying this, we are going to work from the inside out. So we start with the area. Okay. So I want to simplify the area. That always just means do the multiplication. Area is always a height times a base. But I know when I'm working with sums, I do not have a nice rule for multiplication problems. So I don't want to have a multiplication problem. I want to do that arithmetic. So I'm going to say this is the limit as n goes to infinity of the sum as I goes from 1 to n. Now that shell is just sort of hanging out there while I simplify this area. So I'm doing all the work inside of these blue parentheses here. And all I'm going to do is do that multiplication. That's 8i over n squared. Excellent. Okay. So once I've done that, I've simplified as much as I can what's inside of those parentheses. So now I can work my way out. I want to simplify the sum. Okay. So I look at this. This is just one term. I see some i's. I'm liking that. So I want to factor out my constants. So I'm going to say this is the limit as n goes to infinity. Now that shell is just sort of hanging out there while I'm going to use my sum rules to simplify this. I'm going to factor out the 8, and I'm going to factor out the n squared. And I'm left with the sum as I goes from 1 to n of I. Now, this is super, super important. I just treated n like it was a constant, because for the purposes of the sum, it is. My variable for the sum is I. So if I'm working with the sum, I is my variable. It takes on integer values from 1 to n. N is a fixed but unspecified number. But this is a formula for the Riemann sum that I would get if I chopped things up into n pieces. If I plugged in 500 for n, I would get the Riemann sum with 500 rectangles. If I plugged in 200 for n, I would get the Riemann sum with 200 rectangles. N is not changing for the purposes of the sum. I just sort of used it as a generic formula. Sort of like in the formula for the area of a circle. We say it's pi times r squared. Well, any one circle only has one radius, but I don't want to have to say, well, the formula for the area of a circle of radius 1 is pi times 1. The formula for the area of a circle of radius 2 is pi times 4. I don't want to have to give a different formula, so I allow r to represent a fixed but unspecified radius. Same thing here. N is a fixed but unspecified number of rectangles into which I've chopped things. Now, when it gets time for taking the limit, then n is my variable, because now I'm going to change the number of rectangles. So I'm going to get a formula here for the Riemann sum I get if I use n rectangles. Then I'm going to take the limit as n goes to infinity. So n sort of plays a double role. For the purposes of the sum, it's constant. For the purposes of the limit, it's a variable. And that's why we've got to work from the inside out. Because that way, here, I is my variable, but n is constant, I can get rid of the i's by simplifying the sum. Then I've got it down to just one variable n. Okay. All right, excellent. So now I can say this is the limit as n goes to infinity of 8 over n squared times here I'm just adding up a bunch of integers. So remember, if I added the smallest plus the biggest, that would give me 1 plus n. That's what I get for each pair. If I have n numbers, I'm going to have half as many pairs. So what we have, let me come over here, is the limit as n goes to infinity of 8 over n squared times n plus 1 all over 2. Okay, excellent. So there we simplified the sum. So first the area, then the sum. Now we're ready to evaluate the limit. Okay, so I'm going to erase the work we've done so far, but it's always in that order. Work from the inside out, area to sum to limit. Okay. Now, in order to take this limit, it's going to be easier if I have things multiplied out. So this is the limit as n goes to infinity. I'm just going to distribute this 8n to both pieces there. So that's 8n squared plus 8n all over 2n squared. Now this is just a rational function in n. It's not a rational function in x, which is what we're used to working with, but it's a rational function in n. Now, way back when, we actually learned how to take the limit of a rational function. We learned this nifty shortcut that rational functions are dominated by the fraction of their lead terms if we're going off to infinity. And that's true even if I have a variable that's only taking on integer values. So n isn't ever going to be a fraction. I can't have 8.5 rectangles, okay? But n is going off to infinity, and rational functions, whether I'm plugging in integers or any old number, rational functions are dominated by the fraction of their lead terms as n goes to infinity. So I can say this is the limit as n goes to infinity of just 8n squared over 2n squared. Those n squareds are going to cancel, and that's going to be 4. Which is what we said we should get, because this was the area of a triangle whose base was 2 and whose height was 4. So it's very exciting. We got the right answer. Okay. One thing to point out with this limit, it's a nifty shortcut that you can use for rational functions, that you can just take a look at the fraction of the lead terms. Way back when we did this, before we knew L'Hopital's rule, we figured we could formally justify this if we wanted to. I could say this is the limit as n goes to infinity of 8n squared plus 8n over 2n squared. I could multiply top and bottom by the reciprocal of n squared. That would give me the limit as n goes to infinity of 8 plus 8 over n all over 2. This piece would go to 0, and I would get 4. So that was how we formally justified this. I am totally fine. When we're doing limits of Riemann sums, it's a long problem. So I am totally fine with you using the shortcut of just looking at the fraction of the lead terms. What I am not okay with is you using L'Hopital's rule, because you can't. Because this is not a differentiable function. Right, look at that and say, yes it is. It's just going to be, the top is just 16n plus 8. No, it's not. This is a function that is only defined at integer values. If it's only defined at integers, it can't possibly be continuous, let alone differentiable. So if I had x's here instead of n's, so that I was filling in the gaps between the integers, I could use L'Hopital's rule. But when I've got a function that only takes on integer values, basically, I've got a value at 1, I've got a value at 2, I've got a value at 3, I've got a value at 4. That's That's not differentiable. That's just a bunch of isolated points. Okay? And I'm going to be very picky about that because that issue is going to show up a lot in 3B for those of you who go on and take 3B. So you may not use L'Hopital's rule when you have a function of n. You may, however, use the shortcut that if n is going to infinity and you have a rational function, you're just looking at the fraction of the lead terms. So I kind of like this problem because now I know if I ever forget the formula for the area of a triangle, I'm okay. Because I could find the area of that triangle by chopping it up into little pieces, approximating the area of each piece with the area of a rectangle, adding up the areas of those rectangles, and then taking a limit. And that's going to give me the right answer. So I know I will sleep better tonight.